तुझे स्टार्ट कर दो हाँ रिकॉर्डिंग। Hi everyone. So this is the live interactive session for week 11 for the course Structural Geology offered by NPTEL. And the topic of week 11 is ductile shear zones. My name is Rajiv Mukherjee and I am currently hosting these live sessions, and this is the 11th week and we have only 1 week remaining. And due to some unavoidable circumstances, we have to conduct this live session on this day instead of mm, every Saturday. So as we know that we have already covered 10, 10 week of content for the course, and this is the 11th week, and the topic of this week's lecture material is concept of ductile shear zones. Basically it involves some part of uh, fault rheology, fault tectonics, and then it starts with ductile shear zone. So this is the 11th live session on 30th September 2024. Now to talk about the summary of week 11. Week 11 mostly deals with the concept of ductile shear zones. Not only ductile shear zone, but it starts with the concept of strain localization in brittle ductile and brittle ductile transition regime. And so any kind of localization of strain, particularly for natural samples, they can either be constricted in brittle regime or completely ductile regime, or in the brittle ductile transition regime. Now, the brittle ductile transition regime is very much important for us because it helps us to understand the origin and nucleation of deep focus earthquakes, which may take place in lower crust or even in the upper mantle in the plate, lithosphere wedge boundary or interface. So the origin of these deep focus earthquakes are often uh, contributed to the geological changes in the brittle ductile transition regime. And this brittle to ductile transition may happen according to different kinds of deformation mechanism or even changes in phases. So phase transformation is an important factor that plays role in the brittle ductile regime, because in brittle ductile transition regime we are talking about temperatures which are very high, that causes the rocks to partially melt and even cause uh, some viscoplastic behavior. Also at the same time, since the pressure is also very much high, at the high pressure and because of high deviatoric stress, some brittle deformation signatures do also occur depending on the strain rate of the condition. So if we have very slow strain rate, the transition may be very much gradual, and there will be no sharp distinction between a brittle regime and a ductile regime. And if the strain rate is quite high, then we get a very sharp transition between brittle and ductile regime. And depending on the strain rate, the rheology will also change. So there can be two kinds of strain rate. One can be imposed from external factors such as stick slip mechanism or co-seismicity that can certainly increase the strain rate of the deformation. Another is the creep rate of the material itself in a static condition or in a constant gravimetric stress condition. The strain rate the material will manifest will be the creep rate. So depending on the interplay between the creep rate of the material and the externally imposed strain rate and also the temperature, these things will vary. That means the depth at which the brittle deformation regime transits to a ductile deformation regime, it will vary. But nonetheless, localization will remain the same. And localization, as we will see, that it may also appear in the field that localization may take place from centimeters to kilometers of scale. But eventually, when we understand the process, we see that these are mostly controlled by uh, crystal lattice deformation. It starts with intercrystalline plasticity and then evolves into a continuum scale such that in the bulk, rheology changes overall. So we will also look into the mechanisms of this transition or the localization. And apart from these things, we also learned about the progressive evolution of fabric from brittle to ductile regime. We then learned about myelinization of host rock in ductile shear zones, geometric orientation of foliations in myelinized rocks, estimating the effective shear strain in shear zones, kinematic indicators in ductile shear zones, and of course, the evolution of strain ellipsoid in a ductile shear zone. Then, in a brittle ductile transition regime, the evolution of fractures in ductile shear zone. So, this was the mostly the concepts of week 11. Now, the thing is, for today, we will not go for solving one-to-one MCQ problems. Instead of that, we will talk some interesting features, some recent investigations of uh, the strain localization, and we will see that from brittle to ductile within the course of this transition, how different kinds of mechanisms play a role in the strain localization, and apart from their theoretical understanding, how we can also apply these observations or different kinds of empirical laws into estimating some energy budget related to the strain localization or even for earthquake. So today is a blank slide because I will be writing on it. So let us scheme out today's discussion session. So we first say that we will be talking about strain localization today. Now in strain localization, we will deal with strain localization in brittle field, strain localization in ductile field, and strain localization in brittle ductile regime. Now, when we say brittle deformation, we generally mean one thing, which is loss of cohesion. Right. So the loss of cohesion can take place via two important mechanisms. One is intergranular or transgranular fractures. And another is intragranular fracture. So, what is the difference between intergranular and intragranular fracturing? So, intergranular, that means transgranular. So, say for example, there are several grains like this. So, this may be a polycrystalline or a polyphase crystalline rock. That means they are showing interlocking texture. Now, intergranular or transgranular fracturing would mean that a prominent fracture plane will cut across different grains. So they will cut across the grains. I mean, the fracture will propagate from one grain to another. And even though I have drawn that these fractures are merely passing from the center of the grain to just like that, a straight line. But in reality, this is not the case. So if you find a cracked sample like a joint plane or a fracture plane or a fault which is just which is just initiated with the displacement, like those things, and if you make a thin section from out of that, you will see that intergranular fractures will try to follow the grain boundaries. Or cleavage planes, right? So that means if there is an inherent weakness in the system, then it will obviously try to, it will obviously try to activate that weakness when under high differential stress. It will try to activate these systems, and then uh, the fracture will propagate. So this is the concept of intergranular fracturing. Now, if I talk about intragranular fracturing, the same case will happen. So if we have a polycrystalline rock, the same thing, but instead of that, you will see that the grains are fractured. But the fractures are terminating on the grain boundaries. right? Now the thing is, the how these two mechanisms, they help in strain localization. And if we see these kind of fracturings in thin sections from different kinds of rocks that are that are exposed in the field, what inference can we make out from them? Right? So that is the point I am going to discuss. So this is a more of a subjective discussion, but eventually we'll get the idea that how these things can be applied in terms of interpreting the mechanism and the different conditions during this kind of fracturing. So to notice one thing, we can say that fracturing is a process of strain softening, right? Why so? Now, say for example, I am plotting the stress versus strain curve. This is my elastic regime. From there, it is transitioning to the plastic regime. And after that, I can have strain hardening or I can have strain softening, right? What will happen in this case? The sample will show homogeneous deformation and bulging. This bulging is not about the bulging recirculation. It is bulging that the sample will simply try to accommodate the strain in cohesive manner. But whenever there is strain softening, we see that there is some sort of localization. Right? So if we do the experiments in high confining pressure, so say for example, this is at very high confining pressure. So you will get to see the plastic deformations of the material. Now, if I conduct the same experiment at very low confining pressure, so we will see just after the yield, we will see a sudden drop in stress with progressive strain, and at some point we will see rupturing. So that proves that even if we have, even if there is no confining pressure, the material will go under stress release. I mean the material will show stress release via fracturing. Now that is the same mechanism that takes place during strain softening. That means the stress is being released or the energy is being dissipated by the material through localization. So fracturing is a process of strain softening that initiates strain localization in brittle fluid. Right? Now, in the brittle field, the intensity of fracturing will vary with two main components. One is the strain rate, and the other one is grain size. And as a consequence of these two things, we can interpret energy dissipation. Okay. So how strain rate will affect? So first of all, let us not go to strain rate. First of all, discuss about the grain size. Right? So let us say that we have a very coarse sandstone block. Right? This may be a very coarse sandstone. And of the same dimension, we have another rock which is mudstone. Now, if we break these samples just by hammering, okay, we break these samples just by hammering, that means we are applying a deviatoric stress without any sort of confinement. What do you think will happen to sandstone and what do you think will happen to mudstone? So first of all, the question I want to ask is that how clean the rocks will break, how cleanly the rocks will break. What do you think can happen?
In sandstone,
Yeah,
in sandstone, the rocks will be more brittle deformation was there.
yeah, of course. I mean, in both the cases, the mudstone will also show fracturing, and the sandstone will also show fracturing. So because we are not applying any sort of confining pressure, so both of the rock will go under uh, brittle deformation. It will break. I mean, the samples will break. But there is one thing is that the sandstone, if you just break a sandstone, what you will see? A very rough surface. Okay?
Was rough surface. In mudstone,
Very
there
rough
is a
surface.
clean surface.
They have a very clean surface. Because mudstone is fissile, right? You will just uh, uh, just plug them with hammer and you will get clean cleaved mud layers, and they will
Right.
generate very smooth surfaces. But for a sandstone, if you break it, it will generate very rough surface. Maybe there will be some sand dust going here and there around, and you will see that small crumbs of sandstone are also falling apart from the broken area. So, depending on these observations, we can then say that breaking a sandstone will produce much rougher surfaces than a shell, than the mudstone. And the sandstone will also uh, fall apart into several small pieces compared to the mudstone, which will show very clean fractures and fissile nature. So the implications is that the roughness of the fracture surface is controlled by grain size. So if roughness is expressed through root mean square surface height, or undulation, this is proportional to the grain size. So this roughness generated because I mean with grain size is because in I mean, larger grain size. So if you have large grain size, you will have smaller surface area and smaller grain boundary area. And that is the reason that large grain size will produce intragranular fractures. Whereas if you have very fine grain material like the mudstone, like this, very fine grain material cause more surface area and higher grain boundary area. And that is why smaller grains will show um, intergranular fracturing. So this is one of the mechanism that this is one of the parameters that control whether there will be intergranular fracturing or intragranular fracturing. So this is very much clear. One of the parameters is grain size. If you have larger grain size, the surface area will be less, and eventually the total amount of grain boundary shared by each grains, this will also be very much less. And what is the consequences? Because grain boundary is a region of weakness, right? So by increasing the grain size in a given sample, so if you have the same, the dimension of the sample, that means the volume is constant. Now, if we increase the grain size, we will have effectively lesser amount of surface area per unit volume, or lesser amount of grain boundary area per unit volume, and that is why the inherent weakness that are, that is that can be generated through this. The inherent weakness that could be generated through these grain boundaries, it is decreasing. So statistically, the chances of having intragranular fracturing is higher, because only the grains will fracture within, fracture from inside. Right? But if you have a very fine grain matrix, a material which shows the grain size less than say 1 micron in this range, what will happen? The entire material will behave as a homogeneous bulk rock with a single grain. That's the idea. The thing is that in this case, what you are implementing, that you are implementing by decreasing the grain size within the same dimension or same volume. What is happening? The total amount of surface area is increasing. Not only that, but the total amount of grain boundary area per unit volume, that ratio is also increasing. So that means that by default, you are introducing much more defect into the material compared to a coarse grain material. So when you plug the rock with a hammer for mudstone, it will break easily through transgranular fractures or intergranular fractures. But for sandstone, it will break through intragranular fracture, and that is why it will show much rougher surface compared to uh, fine grain rock. Right? Even we can see the examples of uh, granite and the basalt. So if you break a basalt, the surface will be very much smoother, and if you break a granite, the surface will be very much rougher. Yeah, the principle is that with more, very with coarser grain size, the tendency of having intragranular fractures, that will increase compared to smaller grain size. Now, another thing, which is the strain rate. For strain rate, what will happen if we increase the strain rate? Then the strain energy per unit time also increases. Right? So by applying some strain within a certain time, you are providing some strain energy to the system. If you increase the rate of the strain, what will happen? The strain energy that you are applying, the energy that is being utilized to accommodate the deformation, right? You are doing a work, a mechanical work you are doing, because you are applying some force and you are getting some displacement. So force into displacement is the work, mechanical work. And now that you are deforming a rock, That means you are providing some energy through this strain that you are being delivering to the material to accommodate the deformation. Now the strain rate, if you increase the strain rate, that eventually means that the strain energy per unit time that is being provided to the system, it is also increasing. So what will happen if the material gets very high energy in a very short amount of time? This will create very instantaneous release of that energy through transgranular fracture or intragranular fracture. Right? So high amount of energy delivered within a very short period of time will cause the material to dissipate the energy very fast. So since the material will be dissipating the energy very fast, what is the best way to do that? It will obviously find a way, it will obviously try to find a way so that it usually utilizes the minimum effort, I mean the minimum or not minimum, it will try to find the weakest possible path to maximize the devastation or to maximize the fracturing, right? So this is the theory. If you increase the strain energy rate in the material will respond in eventually dissipating the energy in a way, in the similar way. Now, for the material to dissipate that energy in that similar rate, it would require a path, right, a physical path along which it can dissipate the energy in the easiest way. What could be better than the grain boundary path itself? So, by increasing this strain rate, you're eventually transitioning from uh, intragranular fracturing to intergranular fracture. So eventually it will cause right. So if we increase the strain rate, we will have intragranular fracturing to intergranular fracturing. Okay. So what will be the effect of what will be the effect in the localization of this process? Of course, intergranular fracturing means higher energy dissipation, right? With increasing strain. So if we increase the strain progressively, we will see that by having intergranular fracturing, the process of energy dissipation becomes higher. And For intragranular fracturing, what we will get? Lower energy dissipation. Comparatively lower the energy dissipation with increasing strain. So if I then draw the stress strain curve, if I am able to do the experiments in the brittle ductile regime, I may end up producing two curves. So this one, of course, will be intragranular, and this will of course be intergranular. So more the softening, more the localization. So softening is proportional to localization. That means if I have intergranular fracturing compared to intragranular, more localization, and this will cause lesser localization, right? So now the thing is that we see that how the fracturing process is affecting the localization. We can also estimate, we can also comment on the fact that how broad this zone will be. So of course, if we have intragranular fracturing, that means the grains itself are fracturing within it. So it will create a much broader zone of localization. So if we have something grains like this, so the total zone of localization will be controlled by the damage that took place within the grains. So this is a more diffused or broader form where the strain is being localized. Now compared to this mechanism, if we have intergranular mechanism, we may see that the fracturing would take place in a very narrow region. Fracturing and localization in a very narrow region. So in brittle or brittle ductile regime, the localization is affected by the following things. First is grain size, which is inversely proportional to localization. Not higher grain size will cause broader zone of localization. That means, uh, I mean, it will cause. It is. I can say that it's directly proportional to the width of localization. So grain size is directly proportional to the width of localization. That means if we have higher grain size, chances are that the width of localization will be very much higher. Why? Because of intragranular fracturing. The number two is strain rate. It is proportional to the inversely proportional to the width of fracturing, right? Or width of localization. Why? Because if you increase the strain rate, chances are that we will be getting um transgranular fracturing, and transgranular fracturing will eventually will be localized in a very narrow region. That means it is inversely proportional to strain rate. Now another factor is that the strength of the mineral phase. Say for example, we have feldspar and we have quartz, right? So which of the following material will try to say for example, we have a granite, right? So these are feldspar, these are quartz. Okay, more or less this is the distribution. Say for example, now what will happen to quartz? Can you say that what type of fracturing mechanism quartz shows?
Conchoidal fractures.
Exactly. Conchoidal fracture means that quartz doesn't have any cleavage planes, right? So quartz does not have any cleavage. So it will definitely go for intergranular fracture or intragranular fracture. Of course, it will be showing intragranular fracturing, right? Now for feldspar, we can see cleavage planes, right? So since there are existence of cleavage planes, if the feldspars are aligned in some sort of orientation, the cleavage planes will also be oriented, and eventually if you try to break the rock, the fracture plane will eventually follow the weakest path, which is the cleavage planes and the grain boundaries. So the fracturing through feldspar, it will be a mixture of intergranular and transgranular. So feldspar, it will show a combination of intergranular and transgranular fracturing. If I see that the rock contains olivine, what will I say? Definitely the rock will show intragranular fracturing because olivine shows this kind of internal fractures, right? So depending on the strength of the mineral phase and the mineral composition as well, mineral proportion, not composition, the style of fracturing will change, and the style of fracturing will eventually control the width of localization, how narrow the localized channel is or how broader the localized channel is. Now the thing is, why it is important to know that whether the channel is very much local narrower or the channel is very much broader. Simple answer is that it eventually tells us about the strain rate of the deformation or the intensity of deformation. If the intensity of deformation and the strain rates are very high, you will get very highly localized narrow channels of the this localized failure planes and brittle shear zones. Instead of that, if you have a very broader uh, localized zone, broad brittle shear zone, that would eventually mean that the system was going through a more or less equilibrium condition with very slow strain rate of deformation, and that promoted the intragranular fracturing, and eventually the shear zone, the brittle shear zone got spread. I mean, it got thicker, right? So just by looking into the condition, I mean the morphology of the uh, localized zone, in case of brittle shear zones, you can also say that the failure zones, the failure areas, we can comment on the process that how quickly it evolved. If the fracturing was intense with high strain rate condition, this may lead to understand that this fault could be associated with earthquakes. Right? So this is one inference that we can draw from brittle shear zones based on the grain size, strain rate, and the mineral composition. Now, another thing is that the application of these theories of this fracturing. Application of the fracture mechanism in brittle shear zones. Brittle to brittle ductile shear zone. The thing is, uh, let us say talk about fault break shear. What is it? So if we have, if we found that there is a PSZ, principal slip zone of a fault, right? And you're finding clasts, break shaded clasts. So there are some metrics plus clasts, right? Together they produce the break shear. Now, depending on the mechanism, uh, we can estimate how much energy has been dissipated through this fault break shear. So for that, what people do is that they study the grain size distribution of the clasts. So we measure the grain size of the range of grain size, and we measure the cumulative frequency of the grain size, right? So the parameters that study are cumulative frequency of sizes versus the class size. You will generally find this kind of curve. So this kind of non-linear curve follows a power law relation. What sort of power law relation? So if this is N and this is D, N is proportional to D with some exponent, right? So this is the power law exponent. Now if we take log plot, log of N versus log of D, we will get a straight line, right? If we convert this plot into a log plot, we will get a straight line, and the slope of this log plot is called as D minus D, whatever. This is the fractal dimension of grain size or class size distribution. So fractal dimension means this process, how much repetitive the process is in different scales of the observation. Say for example, if I say in macroscopic scale or in hand specimen scale, I get the largest grain which is comminuted or crushed into 4 different small sizes. If this is the process that I am describing at a macroscopic scale, I mean hand specimen scale, now if I just observe through microscope or even through scanning electron microscope in nanometer scale or in micrometer scale, if I observe that in the micrometer scale, the largest class in that scale is also breaking apart into 4 equal dimensions, then I say that this process of grain comminution is repetitive and it is independent of the scale of observation. And this observation of repetitiveness and independent of the scale of observation is called the self similarity. Okay, so self similarity is a process that takes place in each and every scale. That means it is independent of scale and the process remains same in each and every scale. So a process which is not same, if we change the scale of observation, that means the process is not self similar. It is then called a self affine process. That means there are some restrictions beyond which it cannot take place. However, if the process is repetitive in each of the scales, that means if I change the scale, there will be no change of the process or the mechanism, then we call that process as a self-similar process. And according to that, we will get the fractal dimensions. Now, the idea is if you only get a transgranular fracture, right? That means it is running through just the middle of the principal slip zone and just only one fracture. Even though the localization is very much narrower in this case, do you think that the fracture would go on repeating itself in each of the scale from hand specimen scale to microscopic scale to nanoscopic scale and even smaller? Or is it a one-time process only? Any idea on that?
It will not be one-time process.
It will not be one-time process. Why do you think?
So, some stress will always be there.
Yeah, but once the fracture happens, it will release all the energy, right? So, in my opinion, the process will be merely one time because transgranular fracture releases the energy much quicker than intergranular fractures. So, even if the process repeats itself, the fractured zone, which is a transgranular fracture, that means it's a single plane of failure, it may get reactivated, but then again uh, fractures parallel to that plane can never occur again if the fault gets reactivated or the fracture gets reactivated, right? So having a transgranular fracture, it is created one time and then you are applying the stress again, it is very unlikely that the fracture will branch out. It will remain as it is because already there is no cohesion along that plane. So if again a stress is applied, the one thing that could happen is that the blocks across these fracture plane, they will move past each other relative to each other and they will show some slip and eventually it will be called as a fault. Now if the thing happens is that inter if intragranular fracturing is followed by this transgranular fracturing, we will see that the grains will start breaking apart from each other. Right? So in order to produce break shear, not only transgranular fracture is important, but we also need intergranular fracturing as well. And the beauty is that if you plot the log of cumulative frequency of grains of different sizes versus the size as well, and if you get two different slopes, like this, so the higher the slope, high chances of repetitive fracturing via uh, transgranular fracturing and intragranular fracturing. And if you get very shallow slope like this, that would mean, if the slope is shallow, that would mean lesser intensity of intragranular fracturing. So high slope, high intensity of intergranular as well as intragranular fracturing. And if we have low slope, that means lesser intensity of intragranular fracturing. So based on that, L, which is the average clast size, is a function of D. That means the fractal dimension. So if we know the fractal dimension from this class size distribution, we can accurately measure the statistically probable average size, average class size. So by measuring the class size distribution, one can determine the statistically probable mean class size And if we figure out the or calculate the mean clast size, we can estimate the surface energy. If U is the surface energy to produce the total amount of surface energy to produce that particular size of grain. Or the surface energy required to break apart clasts into the size L is actually provided by an empirical relation 6 pi, sorry, 6 not pi, it is 6 gamma lambda by L. Gamma is not the shear strain. Here, gamma is the surface energy per unit volume. Fracture surface energy per unit volume, sorry. And E is a material constant. And lambda is the sphericity of the clast. Because the clasts are nearly angular, so in order to determine, representative radius of these clasts, we need to fit a circle within these dexiated grains to estimate the or to optimize the best fit value, and that best fit value is the lambda, which is the sphericity. So if you calculate this energy, you can use this energy to calculate the seismic moment. Which is m naught. Now, if you can estimate a seismic moment, and if you know that that earthquake, that fault was responsible for some earthquake in previous some years, so you could actually link this grain size as the manifestation of the earthquake that brecciated the clasts, and from the clast size distribution, you can actually estimate the amount of surface energy required to generate that kind of clast, and you can simply uh, mathematically equate the surface energy to the seismic moment, and from that seismic moment you can actually calculate the predict the magnitude of the seismic event. So the localization or brecciation in a brittle fault, this has a wonderful application from which you can actually estimate the seismic moment of the past seismic events through observing the brecciated clast and their sphericity and their fractal dimension. Not only you can comment on the mechanism, whether the intergranular fracturing or intergranular fracturing was dominant, but also we can comment on the energy dissipation, and from the energy dissipation, the seismic moment can also be calculated. So this application I was talking about. So this is a very wonderful application, and I think that as a scientist, you can also incorporate these kind of works in your research since you are going or doing fields in Rajasthan and other region. So there are a lot of brecciated fault regions are there. I have personally seen some of them, And people also do work on the brecciated clasts of different fault in shear zones, especially some fault zones near the fuller shear zone. There are some evidences of brecciated fault gauges. So this kind of study actually you can incorporate to analyze the, analyze the faulting event, and that faulting event can be correlated to the deformation phase of that particular region, and then you can also comment on the deformation intensity with different stratigraphic unit. With respect to different stratigraphic formation, you can comment on the deformation intensity and how this deformation intensity is relating with the phases of deformation and how it is changing. So these brecciated faults, they work as absolute markers, and these markers can also be utilized to understand the energy dissipation during different cycles of deformation. So this was one example that I was talking about in the brittle field. Now, if I talk about strain localization in ductile field, in ductile regime, estimating the mechanism is quite difficult, because in ductile regime, since there is no loss of cohesion, we need to rely on crystal plastic deformations and other kinds of mechanisms, right? So, say for example, we have a ductile shear zone. So, can you comment? Can you say that a shear zone, a ductile shear zone, just like in the previously in a brittle shear zone or brittle ductile shear zone, we talked about that uh, depending on the process of comminution, a fault zone can either be very narrowly localized, or it can even be broader, right? So if we have intergranular fracturing, transgranular fracturing, most likely that the faults, the localized zone will be much narrower, and if we have intragranular fracturing, it will be getting much broader, right? And that also depends on the grain size. Now, in case of ductile shear zone, is it even possible that the shear zone will, can it expand? Can it get narrower? What do you think? What can happen? Or it will it remain constant in thickness? The zone of localization will never expand, neither it will contract, it will remain as the same. So what can happen, do you think, in case of a ductile shear zone?
Sir, today's net connection is not proper. I'm not
Okay, so can you hear me properly or not?
audible, sir. Sometimes it's Why is this breaking, sir?
Okay, okay. So I guess there are some issues with the internet. So I was just saying that in brittle field we are seeing that the shear zones, depending on the mechanism of the faulting, the shear zone can either expand or it can contract. That means it will depend on the mode of fracturing. In case of intragranular fracturing, it will either it will try to expand, and in case of intergranular fracturing, it will try to stay narrower. In case of ductile shear zone, the process is controlled by crystal plastic deformations. Right. So if this is the profile of a shear zone, ductile shear zone, and this is the amount of shear strain, we see kind of a bell curve distribution like this. So these are the boundary of the shear zone. And this is the core of the shear zone. In the ductile shear zone, we see this kind of strain pattern. So this part where the shear strain increases in this non-linear manner, and then again it decreases towards the boundary. This is because of the mechanism which is called viscous drag. Sorry, not grad, viscous drag. So ductile shear zones, they form in viscoplastic and viscoelastic to viscoplastic rheological situation or condition, and when the shear is localizing. So if I just draw so the basic mechanism of shear localization is that you have, so this box type square maybe, and then you deform it like this, eventually it will get a shape like this. So what is happening is that you're dragging through simple shear and the shape is transformed. So that drag, if that drag is instantaneous, that means it starts from the boundary to the core, then again to the boundary in a instantaneous manner. That means if we have a strain profile like this, in this case the viscous drag is less. Now the thing is, more the viscous drag you get, the more wider the shear zone is becoming. So with increasing viscous drag, the distinction between the boundary and the core of the shear zone becomes vague. And as a consequence to that, widening of shear zone can take place. Okay, so the shear zone may get widened. Now, what is the role of crystal plastic deformation in this case? Role of crystal plastic deformation in shear zone widening. So, if you plot the stress strain curve, you see that there are three major states of crystal plastic deformation mechanisms. At the point just after yielding, during the approach towards steady state deformation, and at the steady state deformation. So here we get bulging recrystallization. Here we get subgrain rotation. And then we get grain boundary migration. Right. Now, from bulging to subgrain to grain boundary migration, the entire mechanism evolves in the state that the crystals, they minimize the dislocation density during deformation. Minimize the dislocation density through the deformation process. So obviously, if we go from subgrain bulging recrystallization to subgrain rotation to grain boundary migration, we will get decreasing. We will get decreasing dislocation density. Okay, and what and
Sir, I was
as a result,
disconnected. I was
yeah.
disconnected.
So I was saying that what is the role of crystal plastic deformation in shear zone widening? So the concept
Okay.
is that if you just plot the stress versus strain diagram, so you will just follow that Just after the yield, the plastic deformation starts with bulging decrystallization, and eventually in the steady state it achieves grain boundary
I got
migration.
it. Migration.
And during this process, while going from bulging to subgrain rotation to grain boundary migration, the aim of the crystal lattice is to minimize the dislocation density throughout the deformation. So you will get highest dislocation density at bulging recrystallization, then at subgrain rotation, and eventually at the grain boundary migration. The dislocations will all be dissipated, and the material will come into an equilibrium with the stress. That means it will be ideally plastic. The material will try to be following as ideally plastic. Now, if this is a case of ideal plasticity, if I am to follow a strain softening path like this, a strain softening path like this, so as I said earlier, strain softening may be accommodated through continuously decreasing the grain size and eventually narrowing down the uh, zone of localization, right? In a strain softening situation, the localization will continue through grain size reduction via bulging recrystallization and SGR. But eventually, if you decrease the grain size enough, you will once you will reach the smallest grain size, you can no longer, I mean, deform the material at that same stress. So once the grain size reaches to a minimum value, the deformation can no longer be accommodated. At the same stress level. So what will happen? As a result, the stress has to increase. I mean, to accommodate further strain, the differential stress has to increase. To accommodate further strain, the differential stress has to increase. So what will happen? At a point of time when there is no longer when there is when grain size reduction is no longer an option, from that point it will again start to rise. So it will follow a strain hardening path. This is the critical strain for a shear zone requires to gain to switch from strain softening to strain hardening. So this is softening and then strain hardening. And this is sigma C. So sigma C is the critical yield point, yield strength from where strain softening changes to strain hardening. And epsilon C, this is the critical strain, critical amount of strain required before a shear zone can widen through hardening. Right? So once a shear zone reaches that critical point of strain, at that particular point, the increase in yield strength with decreasing grain size is called the Hall patch effect. So the yield strength as a function of grain size will be the initial yield strength or the critical yield strength plus some factor times d to the power minus half. Empirical factor, and d is the existing grain size. So the idea is that from that point onwards, the material will be following a strain hardening path, and strain hardening, since strain softening is the cause for localization, strain hardening is the cause for widening. Right? So a shear zone can widen provided it has reached the critical strain via crystal plastic processes and it, it obeys the Hall patch condition. Now, what is the utility of the of studying the whether a shear zone is widening or it is softening? So the thing is that a widened shear zone will have much more diffused localization. So if a shear zone in the brittle ductile transition is continuously narrowing down, that means it has a tendency to show some seismic activity or some high amount of slip during localization. And if a shear zone is widening, in that condition, you can say that the event of localization and the simple shear, the shearing, it is coming to cease in a moment. So the growth of a shear zone can indirectly or directly affect the nature of the fault, whether it is in a brittle shear zone or whether it is in a brittle ductile shear zone. Even for myelinization, the grain size reduction is one of the fundamental processes until that point where it can no longer be comminuted, or it can no longer get smaller. And from that point of time, it will be trying to follow the Hall pitch condition that tells us that the yield strength will try to grow inversely proportional to the existing grain size. So this is the mechanism from where the strain hardening starts, and strain hardening can eventually cause seizing of a shear zone at some point of time. And the localization event actually affects the mechanisms of earthquakes. Right? Focal mechanism of earthquake is in most of the cases it is controlled by the localization in shear zones. Right? So this is why studying shear zones are important. And in the field, if we want to estimate the, so for example, we have a shear zone and you have some marker. Okay, you have some markers, and following that you get some stretched pebbles or reliefs like that, or quartz ribbons like that. So if this is the stretched pebbles and it makes an angle alpha with respect to the major foliation, then you can actually estimate the extension or the strain, amount of strain, through the following form. So you can calculate the alpha value, and if you know the alpha, you can calculate the amount of shear strain, right? So if this angle is alpha, then you can say that alpha is equal to half of tan inverse of 2 by gamma, right? So from that, you can calculate gamma. And if you know gamma, you can, this is the simple shear strain, right? And once you know the simple shear strain, you can calculate the extensions, not sorry, extension, it's the stretch of individual pebbles, or stretch of the strain markers. So you will have two different orientations. This is X and this is Z. So X, you will have so X square, the value of the extension along, sorry, so you can write it as Sx. The stretch along x-axis can be calculated as half of half into gamma square plus 2 plus half into root over of gamma to the power 4 plus 4 gamma square, and you can calculate z square as half into gamma square plus 2 minus half into root over of gamma to the power 4 plus 4 gamma square. So this has one of the practical applications for estimating the extension or the stretch of markers that has experienced uh, shearing, simple shearing in a shear zone with respect to the orientation of that marker with respect to the shear zone foliation. So depending on that, we can have antithetic markers, we can have synthetic markers, and the antithetic markers and synthetic markers, they will have different kinds of values of the extension. And from that, by estimating the stretches of these individual markers in every orientation with respect to the foliation plane, with respect to the foliation, yeah, shear foliation plane, you can actually, I mean, estimate how the progressive strain ellipsoid has evolved during the shearing. So this is where you can go from studying the, I mean, from this is where you can go that from studying the finite shear or the finite deformation, you can get an idea about the progressive deformation. Although it is, I mean, a very fast order approximation, but still you can get an idea about the evolution of the progressive strain ratio. So this was about all about today's discussion, where we discussed about the brittle faults and the ductile shear zones and some of their aspects and where we can apply them. And today, and with this, I am currently ending today's discussion session on the ductile shear zones. And the next discussion session, which is on the lithostructural mapping, so that will not take place on 12th October as per the schedule. Instead of that, it will be held on 16th October, Wednesday, from the same time, 4 p.m. to 6 p.m. because I will be in field, and so I will not be able to take the class on the designated day. So I have postponed that class on to 16th of October. So with that, I am currently closing this discussion session. Thank you for joining. Bye.
Okay, thank you, sir.
Yeah.